Hi, everybody. We're PARSEC from Embry-Riddle Aeronautical University, and this is our project, ECHO. Before we begin, we'd like to give a quick thank you to Embry-Riddle and the Undergraduate Research Institute for helping fund our research, as well as the Environmental Health and Safety for helping us conduct safely on campus, and the NIA for helping fund our travel to the forum. PARSEC is a group of 12 undergraduate students and 2 advisors that focus on researching space engineering concepts and develop research and report writing skills through challenges like HuLC. Quick overview of our presentation. We have an introduction with some brief background, our solution, the verification and validation that we conducted, as well as a budget and timeline for future implementation, and our summary. So propellant tracking is the act of actively determining how much propellant you have in your spacecraft throughout the course of the mission. It is extremely important for mission planning. It's used for determining what maneuvers you can do. It's used for understanding how long the mission can be, and it's used for estimating how much propellant is needed for future missions. Now, this is done for all sorts of missions, from lunar missions, such as lunar sortie in this figure, to putting satellites in Earth orbit and even deep space missions. Now, when we talk about propellant tracking, there are 2 main issues that we have to discuss: boil-off and sloshing. Boil-off occurs when heat transfer from the tank into the propellant causes the propellant to heat up, and cryogenic propellants quickly evaporate and can increase the tank pressure. To prevent overpressurization, the tank then has to be vented. Sloshing occurs because of the lack of acceleration in microgravity, and it allows the propellant to float freely in the tank, as you can see in this figure here, from a microgravity test conducted with clear tanks. This can cause a few problems, such as during maneuvers, because it can impart internal moments on the aircraft, as well as determining the propellant extremely difficult, because the propellant no longer makes contact at a single point in the tank and is continuously moving. Currently, there are multiple methods used to determine the propellant in the tank. Some date back to the start of spaceflight, such as bookkeeping and pressure, volume, temperature calculations. And there have also been advancements in technologies such as modal mass gauging, radio frequency mass gauging, and electrical capacitance tomography. However, these systems are still inaccurate, as seen by this figure of an ECT system during ground testing, which still had between 5 and 15% error at times.
Now, prior to further research and development, the team conducted a trade study to determine the best technique to pursue development with. We ranked radio frequency mass gauging, modal mass gauging, and electrical capacitance tomography, or ECT. We ranked them primarily on their innovativeness and the amount of available information. Since ECT is currently being developed for mass flow rate tracking in pipes by companies such as Tech for Imaging, Process Tomography Limited, and Liangstar, there exists a vast quantity of information on not only how to develop ECT, but how to improve ECT. Furthermore, both radio frequency mass gauging and modal mass gauging have currently been applied in a microgravity environment, whereas ECT, according to literature in 2023 by Dr. Story, has as of yet not been applied in such conditions. So, with this rationale, the team determined that ECT best suited our purposes and that we will continue development. To provide a brief overview of ECT, ECT functions by surrounding a region with an electrode array. Then, capacitance measurements are taken between electrodes, as depicted on the leftmost figure. Such capacitance data is then converted into a linear back projection algorithm, typically in typical HuLC systems, and we can develop a permittivity distribution, or a 2D image, off of each section of electrodes. Then, using these images, we can now develop a mass estimate. This process can be depicted on the right. When developing ECT, there faces 2 main challenges: the trade-off of accuracy and the question of speed. For accuracy, if you increase the number of electrodes, you can increase the quality of the reconstruction image. However, if you decrease the electrode size to accommodate more electrodes, you can introduce a significant amount of system noise. Therefore, a careful balance routine must be made for every single system. Second of all, speed. Current reconstruction algorithms, such as linear back projection, as of one, require computationally complex and require a significant amount of time per reconstruction. This can inhibit the capacity for current ECT systems to develop continuous rapid mass measurements. With that in mind, the team is proposing ECHO, or electrical capacitance to high resolution observation. ECHO is a variant of current ECT technology and consists of an electrode array which will line the interior of the desired propellant tank. The electrode array can be customized to fit whatever tank desired, such as Blue Moon and Starship, as depicted on the left. Then, on the right, we have the ECHO operational cycle. ECHO follows the basic framework of current ECT systems by taking 2D permittivity layers for each row of electrodes, and then we send that to our machine learning algorithm. To note, this is where ECHO departs from the currently used ECT system model, where current ECT systems require complex reconstruction algorithms which do computations in order to develop reconstructions. Whereas ECHO is implementing a trained machine learning algorithm, which can significantly reduce the time taken to reconstruct an image and allow ECHO to provide continuous rapid mass propellant measurements.
When the ECHO system takes a measurement, each electrode is excited sequentially. The voltages on all non-excited electrodes is recorded, and duplicate scans are thrown out. This process can be simulated, as shown in our simplified scanning cycle on the screen now. This simplified scanning cycle identifies the percentage of an arc that is filled with a shape's cross-section, which, while not wholly representative of how a physical system would scan the region, provides proof-of-concept functionality. To gather more realistic simulated data, a simulation setup in ANSYS was developed. ECHO's electrodes and cross-sectional inserts are modeled in ANSYS Maxwell, a finite element analysis program that can compute the capacitance between all unique pairs of electrodes. This data is then processed and converted into idealized RMS voltage drops between each electrode pair. This data is then normalized and sent to our machine learning algorithm as a capacitance matrix. The capacitance matrix is composed of 105 unique scanning values. However, if we wish to use an image reconstruction quality of, say, 64 by 64, this dictates that 4,096 pixels must be reconstructed from just 105 measurements. Mathematically, it's impossible. And in practice, many general assumptions are used that may decrease the accuracy of the reconstructed image. This is the so-called ill-posed problem of these systems and is the main barrier to the adoption of ECT widely. To solve this and generate accurate reconstructions, we utilize machine learning.
So the ECHO machine learning algorithm is based on a conditional generative adversarial network which we have modified for this specific use. After the 105 capacitance measurements are taken, they are thrown into a diagonalization algorithm which rotates them counterclockwise into a square 105 by 105 matrix. This is done to make the values rotation invariant, as well as provide a square base for the machine learning model to operate on in later stages. Then the capacitance or measurement matrix is passed into the generator. The generator is a machine learning component designed to take in these measurements and output a reconstruction. Firstly, the generator's first phases are called downsampling layers, which use kernel convolution in order to downsample the image as well as capture high and low level feature maps. Then, at the deepest layer of the generator, we reach the bottleneck layer, which at that point we begin to build back up via a method called upsampling. During this upsampling phase, features are injected from the previous downsampling phases in order to increase final reconstruction quality. Then finally, after normalizing for export, we can see to the right of the generator nameplate in these yellow blobs the reconstructed cross-section. Now, if the model is in a final state, then we're done. We have our reconstruction. However, in order to train the algorithm, another machine learning component is required. That's where the discriminator comes in. The discriminator is a machine learning component that is designed to take in the real cross-section, the capacitance matrix, and the generated cross-section as inputs. The discriminator's goal is to essentially judge the reconstruction with the measurements and ask, is this an accurate reconstruction or does it make sense given these measurements? For each input of a matrix and a reconstruction into the discriminator, it will output one floating point value, essentially representing its confidence that this reconstruction came from these measurements. Then this value is thrown into a loss function and it is back propagated to both of the models for them to update their algorithm weights for future cycles. If implemented perfectly, the idea is that the generator and discriminator will learn at about the same rate so that over time they produce more and more accurate reconstructions as time continues. On the screen is a live reconstruction of the Echo algorithm with its simplified training set. Currently, it has an image correlation of about 95% and an average image error of mass error of about 3%. On the left, we can see our ground truth image, which is essentially a 2D slice of the interior of the tank. Then, after taking capacitance measurements, we get our capacitance matrix, which is in the center. And on the right, we have our reconstruction, which is the output of the generator step. According to a paper titled Liquid Propellant Mass Measurement in Microgravity, while it varies on the type of spacecraft, towards end-of-life phase for a spacecraft, using methods like bookkeeping or PVT, the mass error typically ranges from 3.5% to 10% or even greater, depending on these metrics. Something that should be noted is, although our technical paper mentions a reconstruction time of about 20 milliseconds, this version has a reconstruction time of about 4 milliseconds. And most of the obstacle to the real-time nature of a system like this is actually the rendering of the data to the screen rather than the actual machine learning portion.
Verification and validation is a repeated and crucial process of the project in order to ensure a successful prototype. Thus far, verification has been conducted in order to establish and assess mission requirements. This has included trade studies conducted throughout the entire project, as well as the creation of a verification requirements spreadsheet and a risks matrix. Risk management was considered during development because it is used to determine whether the given system is going to meet the requirements that NASA has set out. During the first month of the project, we created a requirements table as shown here, and it lays out the specific goals that Echo must meet throughout its development cycle. With our current iteration, Echo has already met 3 of these goals, highlighted in green, and for your reference, they're blown up on this image here. The first condition is that Echo is able to derive mass via permittivity measurements, and this is currently being verified through ANSYS Maxwell simulations. Secondly, the system has been proven buildable via our initial testing setup. And finally, the system is of a reasonable mass and size for testing on Embry-Riddle's campus. And if you would like to see our prototype, please attend our poster session tomorrow. Validation is used in evaluating the efficacy of a given system in mass gauging propellant during microgravity conditions. So trade studies have been utilized in order to determine 3 things. Number 1 is the ideal system at hand. Number 2 is which fluid should be used during testing. And number 3 is which machine learning algorithm would be best suited for our purposes. After further research, we then started training a very basic machine learning algorithm using an idealized dataset as well as ANSYS simulations to then validate later testing data. Then a test apparatus was built, which will be discussed in detail later on. Cryogenic testing is the critical next step in order to validate the use of the ecosystem for implementation. This is going to help us to determine the temperatures that the Echo electrodes can withstand, as well as raise the system's technology readiness level, or TRL, to a 5. Then a parabolic flight test can occur in which the system undergoes a simulated microgravity condition. This will further the system to a TRL 6. Following this, we will design and fabricate a more evolved and refined ecosystem, which can then undergo environmental testing in actual space conditions, cementing the TRL of the system at a 7 before full implementation.
I will now be discussing our testing campaign, starting with our testing setup, focusing on our dewar, which is what our whole system was built around. We chose a small 4-liter dewar for its ability to test with cryogenics in the future. We have designed and 3D printed both a lid and 5 cross-sectional inserts that go with this dewar, all made out of a Nylon X carbon fiber filament chosen for its robustness at cryogenic temperatures. We also designed and created a 1x15 flexible PCB electrode array that we've inserted inside the dewar and are using alongside a National Instrument USB 6421 data acquisition system that, along with supporting circuitry, allows us to conduct all of our scans. When designing our testing setup, we had 2 key goals in mind: seamless transition of electrodes and reducing noise. In order to accomplish this, we're using a demultiplexer, which allows us to seamlessly transition between all 15 electrodes inside our tank in order to conduct a complete scan. We're also using pull-down resistors attached to the electrode wires in order to limit stray voltage readings in order to further clean our data, alongside a Faraday cage made out of tin foil, which we've wrapped around the wires that go to the electrodes in order to reduce interference from outside lights, devices, and other circuitry. Then, in data processing, before handing our results to the machine learning, we're applying 2 filters, a Butterworth bandpass filter and a Gaussian filter. The Butterworth bandpass filter allows us to bookend our received frequencies, meaning that we only receive frequencies within a predetermined range, allowing us to weed out early noise. Then, in the final stage of data processing, we're applying a Gaussian filter, which allows us to smooth over the array in order to provide us with a cleaner results. Then, in the very last step, we're able to clip this data array with values below a predetermined amount to 0 to remove all residual noise. Then, now we're going to go ahead and look at the pre- and post-filtered results from our scans on a cross-section that can be seen on the right side of the screen, comprised of 2 cylinders. If we turn our attention to the measurement matrix, we'll notice that it's mainly comprised of greens with very few yellows and purples showing through. What this tells us is that there's a lot of noise being passed through to the machine learning, which becomes readily apparent in the reconstruction, which has several artifacts circled in red, none of which resemble the cross-section which was scanned. In order to account for this, we implemented both filters I previously talked about. Now, looking at the post-filtered results, if we turn our attention to the measurement matrix, you'll notice a lot more yellows and purples coming through, meaning that the majority of our noise has been cut out. And then if we turn our attention to the reconstruction, you'll see that there's now only 5 artifacts, which is not the 2 that we would expect. However, the 2 main artifacts that are being generated do reasonably resemble the cross-section. The other 3 and the slight misresemblance of the 2 main cross-sections we've determined to be in the training data sets that we trained our machine learning on. The machine learning was trained on data sets that did not have noise in them. And so this is leading to misinterpretations when we feed an array that does have noise due to the real world implications of it. In order to account for this, we've been working on training with ANSYS simulations, which have induced noise in order to get more accurate results.
Moving on to the last part of the verification process, we get to risk analysis. Throughout the development of ECHO, we were continuously performing risk analysis to develop the risk priority matrix shown here. In total, we identified that there were 13 risks to consider with our design, and using the matrix, we deemed 4 of those to be critical risks. The first of those risks, shown in the chart in red, is risk 1, capacitor sensor error. This risk addresses the electrodes on the flexible PCB inside the tank. By nature, our system is an analog circuit system which inherently imposes vulnerabilities and challenges to the design that we may not have considered yet. Risk 2, also in red, is thermal insulation failure. Because we are installing ECHO on the interior of the tank, we need to make sure our system can survive the long-term cryogenic conditions, and we are not completely sure yet if our electronics and structural systems will survive. Risk 3, in yellow to signify medium severity, is electrode configuration. Currently, our prototype is a cylindrical tank that uses a rectangular array of electrodes to do all of our measurements. However, if we were to apply this rectangular array to a dome section or a spherical section of the tank, we would have an insufficient number of electrodes to make accurate measurements in that section. And lastly, risk 4 is communication error. Our data transmission system right now is composed of wires and breadboards, so while during testing it's very possible for those connections to come apart, come loose, and we lose data transmission. So now we've identified our 4 critical risks, we also came up with mitigation plans for them. We categorized our different risk mitigation plans into 4 different categories, which are to mitigate, watch, research, and analyze. For our first risk, again, capacitor sensor error, we are going to watch. In the future, we are eventually going to do cryogenic testing with liquid nitrogen to ensure our to ensure our system's functionality. And while we test, we're going to watch how our electrodes perform and then document any events that we hadn't come across yet. And then from there, we'll move on. For BRICS 2, for thermal insulation failure, we're going to research. The main reason we're not very confident with our electronics and structural subsystems yet is because we don't understand all the material properties at that low cryogenic temperature. If we can do research to find those material properties, then we can be more confident and move on in the development of our system. For risk 3, electrode configuration, we can mitigate. When assessing the dome and spherical sections of the tank, we can design new electrode arrays that are customized and fitted to allow for smaller electrodes and maybe different shaped electrodes so that we can get a sufficient number and get higher accuracy measurements. And lastly, for communication error, we are also going to mitigate. This mitigation plan is less so focusing on the design of the system and more about procedures and implementation. So whenever we go to test with our analog system, we ensure all of our connection points are secure so we don't lose data transmission. Yeah, that was it.
And now for our budget and timeline. For our cost estimation, we use NASA's Project Cost Estimating capability, where we base our assumptions on historical cost estimating relationships, specifically from instrumentation subsystems on past launches. We assumed a total system mass of 230 kilograms, which includes the electrode array, electronics, and support hardware. This reflects an implementation aboard SpaceX's Starship. However, the system could be developed at a significantly lower cost for a smaller spacecraft. Plugging in this mass into the first pound cost CER and adjusting for inflation, we estimate the non-recurring costs come out to be $36.5 million, while the recurring costs come out to $5.5 million. This totals to be $42 million. Keep in mind that this budget reflects the full measurement system and not the cost of integrating or launching the equipment. Here we show the full cost breakdown for the development of Echo, totaling nearly $91 million over the next 5 years. This budget accounts for a 10-person team, including engineers, scientists, technicians, administrators, project managers, with salaries and ERE projected annually. Personnel costs come out to be $4.3 million, with the bulk of costs coming from system costs, coming out to be $43.7 million. We take those system costs, add a 50% manufacturing margin coming out to $65.5 million, add that to our personnel costs, and add an additional 30% total cost margin, coming out to the total projected cost of Echo being $91 million. Our 5-year plan for Echo is structured around key phases of development, each with built-in margins to reduce risk. We begin with 14 months for additional testing and preliminary design, including a 2-month margin. Then an 18-month phase for detailed design and system integration work with 4 months of further margin. Finally, we allocate 27 months for integrated and environmental testing with 6 months of margin. Each phase aligns with major reviews to ensure progress towards a flight-ready system by November of 2029. Now for our conclusion. Over the past year, we have worked to take Echo from concept to a prototype capable of demonstrating mass gauging through capacitance-based sensing and machine learning. We simulated our design on ANSYS and conducted experiments using a scaled-down proof-of-concept setup, where we have incorporated simulated data to train the machine learning algorithm adopted. The machine learning algorithm is capable of performing proof-of-concept area reconstruction with preliminary array results. Overall, we believe Echo has strong potential for continuous and accurate mass gauging in the microgravity environment. And moving forward, we would like to conduct cryogenic testing to further verify and improve Echo's design under relevant physical and chemical conditions. We also plan to obtain a variety of more complex data sets to then adopt other machine learning models in order to increase our accuracy even further. Lastly, we will introduce additional layers of electrodes to enable 3D reconstruction for the deduction of mass from the system. These steps will move Echo further from being a prototype to being a flight-ready system, reshaping the way we measure fuel in the harsh environment of space. With that, this concludes our presentation. Thank you for your time.
Thank you so much. That was Embry-Riddle Aeronautical University Prescott and their Project Echo. We'll now go to the Q&A session, and we'll start with Reed. Reed Ruggles.
Great presentation. I am not an EE, but you made me understand all this kind of stuff. So I have no background in it.
Either.
You did a great job. It's a really complicated topic. This kind of stuff is super interesting as well. I was reading through your paper, though. One of the biggest questions to me is, this seems like something that is currently used, if I understand correctly, in like piping systems, maybe on the ground for oil and gas or whatever it might be. What are the complexities and the issues you see with scaling up to, say, a 9-meter diameter tank? I know you had a statement in there, something along the lines of your excitation voltage and all kinds of stuff is going to have to go up by some amount. How high do you see that going? Again, not an EE, but I can imagine that like inverse square law comes into play if you're trying to pass, electrical current across a very large tank, and you might have some issues. But any thoughts of what a flight system might encounter?
No, you are absolutely right. There will be
Not far
losses. We have looked into this, and we believe that an increase in voltage and higher frequencies should allow us to overcome the challenges of that. One of the amazing things about ECP systems is that they are incredibly low power. Very small systems, might be it, have been designed that use up to 10 watts of power. Because of the low current that's required to operate these systems. They operate almost entirely on a change in voltage.
I really like the trade study you did up front where you looked at multiple different solutions before jumping in and choosing one and going all in on it. One question I had on the modeling of the system, did you look at any sensor out scenarios, like if you had a sensor that failed, how that affected the response of the system?
So while that is not something we have simulated yet, that is something that we're aware of, and that is one of the risks that we are tracking as well. The fact that if a sensor were to go out or maybe it were to be damaged, then that changes the data that the algorithm is receiving. So essentially we would have to train the algorithm to detect when a sensor goes out and then be able to operate without that sensor.
And if I can add on to that really quick, I was in charge of working the testing setup, and during testing, as Jacoby had mentioned in our risks, because we're working off a breadboard with wires and stuff, we did have one come undone that I didn't realize during earlier stages of testing, and that data did slightly influence the reconstruction and make it slightly worse. However, it wasn't to an extreme amount, and so it is believed, at least so far with what research and experience we have, that it is plausible to function with an electrode or two out and still be able to give semi-accurate readings.
Okay, thanks.
Thank you, students in black. I'm intimidated. I thought I was going to ask about risks. So I think I heard you say you got down to the 4 out of X number that were in the slides, but I wasn't sure if you wanted to expand on how you got to the 4.
Or well, for sake
4.
of time in the presentation, we still have all 13 risks to consider, but those were all of the highest priority, highest concern that we need to mitigate first before we start addressing the other ones.
But how did you come to the conclusion about those 4 being at the top of your list? Was there a particular process? Was it just conversation, judgment, any analysis?
We used the risk priority matrix there, if you want to go back to it. On the x-axis, it was, well, we risked both the likelihood of that event happening and then the consequences if it were to happen. And then we ranked them on a scale from 1 to 5. And if both were at 5, that would be the most critical risk in red. So that's how we got 1 and 2 to be high severity risks. It's just by ranking likelihood and consequence.
Across all of the much larger list of risks that you had previously
If you go to the
had.
appendix as well, we have all 13.
Yeah, I glanced ahead and I saw that. So you just went through each individual one because those came out in the risk matrix that way. They emerged as the top 4 by just applying the process.
Yes,
Great.
sir.
Thank you. Oh, yeah, there we go.
Oh, me. Thank you. This is a really good presentation, so kudos for you. This is almost exactly what we look for in kind of these low TRL technology development efforts. So,
thank you.
Congrats. One of the questions I had is the system dependent on a kind of a continuously smooth sensor array? I say that because in kind of once you scale up to large scale tanks, you're not really going to have that smooth kind of inner walls. There's other Those are the systems at play, either feed lines or slosh baffles or even the construction of the walls themselves.
I'm glad you brought this up because this actually highlights one of our main advantages to using machine learning is the versatility. The nice thing about utilizing machine learning algorithms is that we can train and account for errors in tank geometries such as slight wrinkles or maybe the electrodes are slightly off where they should be. The machine learning should be able to account for that. You also mentioned tank baffles. The nice thing is when implemented, the ecosystem can have separately trained sections of the machine learning algorithm for separate parts of the tank, including domed geometries or regions of the tank with baffles. And in those regions, the electrodes will specifically be trained for data within those regions and be able to account for those weird geometries.
Awesome.
Okay. Yeah, excellent presentation, especially with respect to the signal processing and how you plan to go through that, and some of the simulations were really good. I'd really like to hear more about the analog portion, the electrodynamics of what's going on there with the, like how are the electrodes excited? What voltage levels, what sort of signal there? What about backguarding? Do you have to backguard the various electrodes? How is that done? And how's the capacitance signal actually measured? You know, the analog aspect.
Yeah, so of course. So for our system, what we're using is we're exciting with 3 volts across a square wave that's being excited at 1,000 hertz. This was done due to the DAC itself being able to get a sample rate of 15,000 samples per second, which maxes out the DAC's capabilities, but allows us to get a 10 to 15 times larger sample rate compared to our frequency in order to get more accurate results when scanning a tank like this one. And so we're using 3 volts currently, and for this setup, we have our single ring of electrodes, and then on either side, we have guard electrodes, which are grounded in order to limit stray capacitance readings. And in this setup, we're not actually using the capacitance reading itself, we're using the voltage drop, and from that, we're able to normalize into the form that the machine learning is expecting, if that answers your question.
Okay, yeah, so you provide a pulse, square wave pulse, to whichever electrode is decided to be excited at that point. The other electrodes are being held at ground potential, or they're probably shunted to ground through a high impedance resistor, and then you measure the pulse detected on each of the other electrodes.
Yes, I'm not an EE as mentioned. I'm an AE, and first year, I've been learning all of this from the ground as we built this testing setup. Okay. So I don't have a very great answer to your question, but if you come to the poster session tomorrow, I'd love to look at the circuit with you and talk through it more, and I might be able to provide you a better answer then.
Okay, that'd be great. Yeah. Thank you.
So is this the type of electrode system that you're going to be using in an actual tank?
So this is a scaled down version of such an electrode system that's been designed specifically for this tank. A full-scale implementation would look very similar to, if I can get to that slide quickly, very similar to this, where we would have several electrodes lining the entirety of the interior of the tank, but each of them would be completely around the tank, and they would be staggered so that we can measure across all of them.
So they're PCB based?
So we are currently looking at multiple different designs. For this design for our testing, we are using a flexible PCB made with polyamide as a backing, but that is simply because that was the easiest way we could get it to be manufactured. It could possibly be used in a full-scale system. Polyamide is known to handle cryogenic temperatures, at least from the research we have found. And so that is a possibility. We've also looked at possibly integrating the electrodes into the tank walls, but that would require major changes. So it's still in progress, and we'll learn more about that over the next year as we continue development.
So for a much larger scale array, we could use polyamide, and We could use a process known as chemical or physical vapor deposition, where you would have like a gaseous copper or aluminum, for example, that you would deposit onto the polyamide film, and then you would have a very thin layer of electrodes that you could deposit. And that's a way we could manufacture an array at a very much larger scale.
So all the wiring would be within the film itself, or where are the electrodes going?
Yeah, absolutely. That is a great question. And that is something that we have been considering. As Bruce mentioned previously, one of the future iterations that we are currently looking at would be to integrate the electrodes into the walls. And so the wiring would also be in the walls. And that ensures that nothing is exposed to cryogenic fuel messing with measurements.
So are the electrodes then coming out of the wall, or are they run along the wall? Or?
Yeah, it would be inside running out then. It is something that we still have to do more research into, but we are very excited to take the project further this coming school year.
And for a large tank like that, how many electrodes would you need?
Yeah, that's a great question. And one really great advantage that we have is that it's not simple, but it's very feasible to recreate an electrode array in ANSYS simulation, for example. And like I was mentioning priorly on the slide prior, since there is this trade-off between resolution and system noise, we could spend a significant portion of time involved in simulations to determine the most optimal array of electrodes, be it like electrode size, be electrode amount, etc.
Is there online?
Sorry?
Does Esther have a question?
Not yet.
Okay. I've got another one. So let me find my question. Where is it? Do you have an idea if you made, ideal assumptions, like for the flight vehicle, everything works like you think it should, you can put the electrodes in. Do you have an idea of what the ideal uncertainty number is for your mass value? Because I know you mentioned you have some literature where spacecraft in whatever other systems are like 3 to 10%. I think in kind of HLS world, we're more thinking probably more like 1% or less. If you're really worried about, hey, you got to use all your mass, you got to use it efficiently, especially for human spaceflight. So do you have any idea of what is the ideal number that you're trying to get towards?
Yes. So we have research from credible sources that states that an ECT system measuring a specific volume of mass, not like a flow rate, can be accurate to within fractions of a percent. I believe the report referenced around 0.2%. And we believe that with further time and specifically more information given to the machine learning, we can continue to increase our accuracy to that point.
In the fluids testing trade chart that you showed, it was probably like chart 2 or 3.
Yeah.
How did you assess, I guess this goes along with, how did you assess the accuracy? Yeah, so in the paper you had 2 trade tables. One was the different methods and the other was the fluids. And I was wondering on the fluids one, how you assess the accuracy of the different fluids.
Yeah, absolutely. So one thing we looked at is permittivity and how it would react with the electrodes in order to get an accurate scanning. Another thing that we did look at was time constraints, because we were going to do testing during the last month of our semester on campus. We unfortunately couldn't really do liquid nitrogen, even though it scored very high on our trade study. And so because of that, we moved to the next best option, which was air. Anything to add?
Say the liquids in that trade study were chosen because they are safe to handle. Again, we were restricted to testing on campus and had to work with environmental health and safety. So all of those went through them. And as we did attempt to test with liquid nitrogen, unfortunately, you guys know how boil-off works. It all evaporated before we got to start testing. And so when we went to make our measurements, we were disappointed to just hear gas coming out.
Yep. Nothing online. Good to go. Okay. 50% manufacturing margin. Where did that come from?
Yeah, so a couple of us on this team have actually participated in a prior mission concept training academy called the LaSpace Mission Concept Academy through LaSpace. And a lot of the budgeting margins that we used, we also learned to use through that sort of process that they taught us, which was modeled after NASA programmatics budgeting standards. And so that's kind of where that came from, was the budgeting that we did back during that project.
Thanks.
Yep.
All right. We do have not a question, but a comment from our online judge, Esther Lee. She says, "Great job. This is a really great concept." I think
Thank you, Esther.
you've answered the question. All the judges have already asked all of the questions that she's had. All right.
I've got another one, sorry. So if I understand correctly, you are pre-training the ML model on the tank geometry before you go and do the live readings, correct?
That is correct.
And then you're using that to get your mass readings.
Yes.
You're just, so you have the pre-trained model, you get it, simplify it, get an equation, right? You put in the numbers, you get out, hey, this is how much mass you have, right?
So we're currently working on using ANSYS simulations to get as close to accurate models as we can. However, the system will still need to be calibrated. It's not going to be accurate right off the gate.
Right.
And so we will need to do additional testing with known quantities of propellant in a tank that is at least analog to what we'd be working with.
Okay, that's what I was going for. Because so obviously when you put cryo in the tank shrinks slightly. So that's going to change what your ML model gets out. When you pressurize a tank, it also grows slightly. You're going to have issues with that. If you're measuring under acceleration or under thrust or something, you're also going to get bending and different weird things. So that's good to hear that y'all considered that.
Yeah, and just to add on what you just said, that is why cryogenic testing is one of the next steps of our project in order to see exactly how this is going to work in real time in a hands-on environment. And that is also why we are looking into the properties of copper electrodes and specifically how it is going to handle cryogenics.
Yeah, side comment on that, for hydrogen, the copper will be close to superconducting, so that might get entertaining. If you go back to chart 18, yeah, there's a couple of these that it looks like either the verification or the requirement hasn't been verified yet. Is that what the not yet isn't trying to say?
Yes, that's correct. The not yet is signifying that the requirement has not been met yet. However, all of these we are going to continue working on as we develop the project.
So from analytical or from an analysis perspective, are they all met, or are some of these just like as your design sits today, there's none of these that you project that you won't meet, is what I'm trying to ask.
Yeah, so sorry, just give me 1 second. I haven't read these in a while because I've been busy practicing. But yeah, all of these should be completely greened out by the end of the development cycle from the timeline that we proposed during the presentation. So all of them will be met.
Okay, thank you.
Thank
At least
you.
we hope so.
Do we have any additional questions from our judging panel? Absolutely.
How did you attach your electrodes to your sample doer?
That's a great question. I wish David was here because he'd really enjoy talking about that. Do you want to talk about it, Ian?
Well, let me ask you this. Once the nitrogen boiled off, did it delaminate? Did it come off of the wall?
So the liquid nitrogen actually boiled off before we were even able to begin putting it in the dewar. It boiled off in the dewar that it was delivered in. It took us an extra day to get ready for testing than expected, and by that time, all that was left was gaseous nitrogen.
Thank you. Excellent presentation.
Thank you. Other questions from our judging panel? Quick ones? No? We have 30 seconds.
So following up on what Ali said, do you have a plan for how you would structurally attach these to the tank wall?
For the scaled prototype or for full-scale implementation?
So you showed a mass of 230 kilograms, but it didn't look like it included any structural attachment to the tank wall.
I'm going to invite Embry-Riddle to answer this question during the Q&A session for all of our judges. And thank you so much for presenting.
Thank you.